Good morning. Normally, I always start with my talk like saying it's a pleasure to give this talk. Unfortunately, I cannot say this time because this talk is supposed to be given by the postdoc, the young postdoc from Vanderbilt University. He just started his position there a few months ago, and he was advised by university not to travel outside the U.S. during this turbulent time. Nevertheless, it's still I have to thank the organizer for this exciting meeting. I'm very excited to talk about the physics about diffusion wake in heavy ion interactions. The jet quenching, of course, is a fact. We have seen that since 2001, when the day that Rick started taking data and showing the results. And it's mostly illustrated by Atlas that you can see apparently there is a jet quenching by comparing to PP versus AA. But the question still lingers that where does the loss energy go? And how does loss energy redistribute as they propagate through the medium? So not long after that, there's a couple of proposals come on that propose that this energy deposited into the medium acts like a source of perturbation in the dense QCD medium. And they propagate more or less like a sound wave. Of course, the speed of propagation of jet speed of light is much faster than velocity of sound in that medium, and that will produce the so-called Markov effect. And this has been later on verified by hydrodynamic simulation. And you can clearly see the shock wave in front, and then if you see it in the back, look back, there's a so-called diffusion wake. The diffusion wave is nothing but the depletion of energy of particle in the medium because of the recoil, the back reaction process going on that is left behind the jet. This actually field work is essentially spurred by the measurement you see by Phoenix. They measure at the time two particle correlation, and then in addition to the V2 you see, and then they also see another bump in the middle, and this is why there's a speculation of this Markov effect. And of course, a few years later, this article came out and taught us that the nuclear is not exactly perfect a sphere, but there are fluctuations, and those fluctuations can lead to geometric fluctuation, and that can lead to anisotropic flow, which essentially gives you this V3 effect. And I have to say, this is the theory paper written by experimentalist, and that has most citation I know so far. And then at the same time, there are a lot of realistic numerical simulations that you can see produced Markov, but there is no sign of such angular structure in two-particle correlation. So the question is why and how we can see that. The fact that there has to be such a simulation, like medium response, but this is I just give you one example that even in transport calculations, like linear Boltzmann model, and if you send a particle, a single particle going through the z direction, the recoil particle interact with the medium, and then the energy will redistribute it really like a Markov effect. This linear transport model is just using the Boltzmann transport and linearized only consider the interaction between jet shower particle and the medium, and you neglect the nonlinear effect between, for example, So we simply take this, everything is considered perturbative, including the 2 to 2, 3 process, and also 2 to 3, 2 to 5, with induced radiation given by high twist approach. And most importantly, we do allow the recoil parton to rescatter again, just like the jet particle. So that's, you can see that's why there is propagation of the energy excitation through the medium in this Boltzmann approach. And then, of course, since jet is a 3D structure, you do need a 3D type of hydro to facilitate this kind of simulation. And further, you can go further and say, okay, if you don't trust the perturbative 2 to 2 scattering or 2 to 3 scattering anymore at very low energy scale, and you can do a cutoff, said below that cutoff, I think they are strongly coupled system. I will let the hydrodynamic take over, and those energy deposited by these low partons, low energy partons, are essentially act as a source term into your hydro, and you feed back into the system and let the system evolve concurrently. And that's what this coupled LBT will do for you. And here is an example what you see that. And this is a real event with non-central interaction of lead, I think lead, with a Z jet. And this Z goes into that direction. You can see this is essentially there's energy density because it's not uniform in event by event hydro. And then this is the final jet coming out. And if you do the same kind of simulation of hydro without jet, and then afterwards you subtract it to what you see essentially on the right, that is, you can clearly see the wake front of this excitation, and then you leave behind, and this green is essentially negative, means that's really the diffusion wave you see. In addition, you do see some structure. There's a clearly correlation between the wake front and then the particle that is not quenched completely and came out. I will come back at the end of this talk on what that correlation tells us about. The immediate consequence of this medium response is you can see that if you look at the jet shape, and you look at the jet shape as function of the radii, and normally without recoil, you can see there's enhancement here. So those enhancement in the at large angle essentially is contributed by mostly soft hadrons, and that you can see from the fermentation function. So you can see there's enhancement for small soft hadrons, and then of course for leading hadron they are suppressed. That's due to jet quench. That's just simply jet quenching. This enhancement at large angle soft hadrons, they have essentially two contributions. Now, in addition to the medium response, you should also expect the hadronization of induced radiation that come out too. So in this case, it is very hard, almost impossible to separate them. If you see this enhancement, you have no idea which part is coming from the medium response and which part from induced radiation. And that's why we thought that by looking at the diffusion wave in the backside of the jet could be very useful, because there is no corresponding counterpart in other processes that give you a depletion of particles in the medium. And CMS actually look at, apparently you want to look at in azimuthal angle, and you do see after the subtraction of the MPI contribution, and you do see some kind of suppression, depletion, but that's really, really tiny in this azimuthal angle correlation. And so we were, at that time, we were lost. What can you do? But it's still not tiny in fact. And then we come back to the fact that jet is a 3D structure, is a 3D structure. not only you should see some correlation in azimuth angle, maybe you also look at the rapidity correlation too. So indeed, in this coupled LBT, we looked at this like correlation, this jet hadron correlation essentially, in both rapidity and azimuth angle. And in PP interaction, this is the gamma jet. I think this is gamma jet. In PP interaction, you do see in the opposite direction of gamma, this is the jet. It is there. And then you can also see this underlying MPI. This is from multiple particle interaction. Multiple MPI is nothing but just independent mini jet production coincidental to your jet production. And that's why it's independent, so it's uniform in azimuthal angle, but has a particular structure in rapidity here. And then if you look at in heavy ion interactions, first of all, the jet peak is enhanced because the soft particle come from medium response from the Yamaha cone and the induced radiation. But in the meantime, in the gamma direction, you do see a valley is developed. That's the depletion due to the diffusion wake. And this is really, really clear. And once you do the projection on this side in rapidity, you do see the double bump. This is double bump essentially is a contribution from the MPI here, and then also the diffusion wake, the dip. And you will see the talk by CMS, and they do find such a unique structure in rapidity too. So that is ambiguously the signal of diffusion wake. If you do some force selection, select the gamma jet asymmetry with smaller value, this means that you have large energy loss. With large value, it means that you have less energy loss. And you can see the depth of this diffusion wake valley definitely is proportional to, it's very sensitive. Means that you have, once you have more energy loss, you do see a much stronger effect in the diffusion wake. So, and then, of course, what happened in the dijet? Dijet is tricky because you have back-to-back jet. The diffusion wake of one jet is completely overwhelmed by the hadron from the other jet. It's very, very, very difficult. And then Danny Pavlos proposed, maybe you long ago, that he proposed this, what happens if you have jet with rapidity gap? So once, in event when there is no jet gap, there is, you can see that this is one jet with no diffusion wake. But if you add on diffusion wake, what it does is simply bring down the correlation a little bit, but it's not really very interesting. But once you have a rapidity gap between these two jets, suddenly the diffusion wake from one jet is different, it's in different rapidity region of the other jet. So suddenly you see this particular rapidity distribution. So this is very different with this. And what happens, what do you do? You subtract, you look at the difference between these two events, and what this is what we call the rapidity asymmetry, and you can clearly see this particular rapidity asymmetry coming rise because of diffusion wake on one side, and then there is a less reduction of the peak because of the presence of diffusion wake on the other jet. So depletion and enhancement, both because of the diffusion wake in dijet events. And indeed, that's what we see in this real simulation. And if you look at events with rapidity gap, without rapidity gap, the difference essentially is characteristic as we have imagined it should be, both in the triggered jet and in the subleading jet too. They both actually have this particular asymmetry. I want to emphasize this is very, very exciting because this does not require do background subtraction, because the background in both this gap with not gap essentially is identical. When you look at the difference, the background completely cancels, and what you see essentially is caused by the diffusion wake. And further, if you look at jet shape, now jet shape you will not only look at radial distribution, but also azimuthal angle, which we call differential jet shape. And I told you earlier that the high-pitted jet have some kind of deflection because the gradients. And this is exactly in the opposite azimuthal direction of the soft hadron coming from the diffusion wake. So if you look at the azimuthal angle distribution of the jet shape, you will see this particular depletion for the, not depletion, it's a correlation for high-pitted particle, which is in the opposite direction of the soft hadrons here. So this is a particular correlation between high-pitted particle and soft particle within your jet shape. So this is what we call a symmetric jet shape. And if you let the jet sit in a large rapidity, this feature is now shifted to some larger angle here because of this particular rapidity requirement. And that is enhanced due to the coupling to longitudinal flow. So in this case, not only you see the diffusion wake, but also they see the effect of the longitudinal flow. Okay, and I will further just give you back. We also did some kind of deep learning technology, method, so to help you to select events in a particular position. So in that case, you maximize the effect of the diffusion wake too. So in summary, the medium response is a very important part of the jet event in your heavy ion interactions. It leads to enhancement of soft hadrons in jet direction, but also depletion of soft hadrons in the back direction due to diffusion wake. And there is this unique 3D structure of diffusion wake that makes it easier to detect, to see. And finally, the rapidity symmetry can be a very robust signal of measuring diffusion wake because there is no need of background subtraction. I think there's a lot of study we still have to go on to, in particular, trying to use the diffusion wake and the medium response to give us kind of constraint on equation of state, for example, and on the transport coefficient. Thank you for your attention.
Thank you very much, Xin-Nian. Floor is open for discussion. Corinna, please.
Yes, thank you. This is very interesting. I have a question, and that is, already without your hydro simulation, you would get a depletion of soft particles opposite to the jet because the recoils will be co-moving with the jet. So do you have any thoughts on how a hydrodynamic response can be distinguished from simply momentum conservation?
We have two versions of this simulation. One is purely LBT, which essentially is, there's only particle scattering. There you see also the effect of the recoil. You see the wake front and the diffusion wake. It's just that we don't trust that kind of simulation as much as coupled LBT because we think at a very low energy scale the particle interaction is properly strongly coupled, and it's better to handle that with hydrodynamics. In coupled LBT, we separate these two. For energy scale larger than certain, we let the LBT works, and once at low energy scale, we let hydro. And the final result is not much dependent on the cutoff because the energy conservation essentially is ensured in both approach.
Second short question by Bernd.
Yeah, my question is very much in line with Corinna's. I can, of course, think always of transverse momentum conservation, right? Now, normally in a vacuum jet, we think that the transverse momentum is balanced by the other jet, the back jet, right? And it has the same narrow angle distribution. In the presence of an environment, like a nuclear collision, of course, that distribution could be wider.
What?
Could be wider in delta eta, for example, or...
You mean ecoplanarity, so I'm talking about?
No, what I mean, just the back, balance momentum on the other side of a jet
Yeah.
can be wider in delta phi and delta eta than it is in vacuum, right? And how do you distinguish this from a particular mechanism for that, which you call the diffusion wake, right? One would be just momentum broadening of the backjet, or the back momentum distribution, the balancing momentum distribution. The other one is a specific mechanism. And one way to do that is to say, we can look actually at the different flavor composition of the jet fragments and those that actually come from the medium. Can you try to analyze this in your context and find a way of actually somewhat model independently show that this, what you see, if you see a structure like this, is actually a diffusion wake and not some other phenomenon?
Well, you're talking about flavor, the flavor of the. Yeah.
We need a short answer.
Yes, the short answer is that in the calculation we look at the particle spectrum coming from diffusion wake or from the medium response, which resembles like a thermal emission rather than from the jet. Okay, you can actually extract average temperature, which is a little bit higher than the environment because of the energy you're depositing into too. The answer is, I don't know how they do that in experiments. Maybe similar way you can identify. Yeah.
So I think we thank Xin-Nian again, but I would hate to stop this without flashing again the name of the young collaborator who was supposed to give this talk. Possibly you say at least